Hello and welcome to 3.2 Linear Functions. We are going to be working on pages 54 and 55 in your student companion. Please use the blue margins in your student companion to take notes and write down any examples and important vocabulary words. How can you represent a function rule? So right here it says write the equation y equals 5x plus 1 using function notation. Remember that a function is a rule that takes an input or an element in the domain and maps it to an output or an element in the range. I'm going to show you this little animation here. This guy right here is a function machine. It's going to go ahead and show you that what you do is you take your element here, x, it goes into the function machine. This is your rule, and then it comes out as your output. In this case, our output is called f of x. This little f with a parentheses x is called f of x. Now, in the past, we used to call output y for linear equations, but for linear functions, we're going to go ahead and use this function notation here of f of x. Function notation, the reason we have it is because it's a method for writing variables as a function of other variables. We like to use function notation because it is helping us if you end up having a graph here and you have two lines on that graph. Let's say that one of them is this equation right here and another one is a different equation in the same slope-intercept format. It's sometimes hard to tell what's a part of this line and what's a part of that line, which one is line 1 and which line part is line 2. But if we use function notation and label one of the lines f of x, we can use g of x to label the other line. So maybe f of x is line 1, g of x is line 2. And then it's easier to distinguish between the two lines. So that is why we have our function notation. And in this case, we're going to look at linear functions, which specifically have to do with slope-intercept format, which we are very familiar with. So we are here we're on page 54. This is going to be in one of our examples before we get to the ones in your textbook. But we are going to go ahead and solve. What is the value of g of x equals 5x plus 1 when x equals 3? So this is going to be very similar to solving linear equations, where we are just going to take the information that is given to us, that x is 3. Oops. And we're going to use that to solve this function instead of a linear equation. We're going to substitute 3 as our input. We are then going to solve here, follow this rule. So if x is 3, then my rule is now 5 times 3 plus 1. So 5 times 3 is 15 plus 1 is 16. And we then get our output of 16. So if g of x equals 5x plus 1, then g of 3 equals 16. The g of 3 means that the value of the function g when x equals 3. So all we're doing here with this function notation is trying to learn how it works so that when you see it in a problem or a test, you know what to do. So if you see a question that looks like this right here, okay, like this one right here, all you need to do is substitute the x for 3 and solve, and you can write your solution like this. So let's practice. So here we're going to go ahead and evaluate each function if x is 4. So I'm going to type it out so you can see. G of x equals negative 2x minus 3. So now I want to know what is g of 4 going to equal to? Well, it's going to equal to negative 2 times 4 minus 3. So now I'm just going to solve. G of 4 equals negative 8 minus 3. So G of 4 equals negative 11. I'm going to check our answer, and we are correct. Go ahead and solve problem B. So just so you know, these are the try-its that are on page 54 in your student companion. Go ahead and try part B on your own, and we'll check it in class. We are now going to move on to example 2, which is also on page 54. We are writing a linear function rule. So we're going to remember this is an example that's not on your page, so you can take notes in the blue section, and then we'll do the examples in a minute. The cost to make 4 bracelets is shown in the table. How can you determine the cost to make any number of bracelets? So what we're going to do is the very first step, and I would write these steps down, is we're going to examine the relationship between the values in the table, because we want to make sure that this relationship is linear. So as you can see here, when I skip count through my cost, I can skip counting by 15s. My number of bracelets is going up evenly by 1, which means that my constant rate of change is 15. So every bracelet that I make costs $15. Now, because this is not 1 to 15, I know that this is not a proportional relationship, that there is some sort of initial cost or initial starting point, which means I'm going to have a y-intercept or a b. Step 2 here is now to write that function. So again, just like we would write normally the linear equation, y equals mx plus b, instead I'm going to write the linear function of f of x equals mx plus b. I'm going to take my rate of change from my table and replace it as m. And now the last step is to solve for b. Just like in our last topic, we're going to go ahead and do some substitution in order to find b. So they took the ordered pair here, 1, 17, and they replaced them for x and what would be y, or f of x. When they solved that right here, they got 2, which means that b is 2. And you can tell from up here, because the difference between the rate of change and this number here is 2. So I know that the one bracelet, even though it cost 15 to make, there was a charge of $2 there, an initial cost on top of the 15. We're then going to use the function f of x equals 15 plus 2. That is now something we can use to determine the cost to make any number of bracelets. As you see, this function is a linear function because this rule right here is the same as this linear equation rule right here. So let's go ahead and try some on our own. All right, so these are the problems that are on example 2 on page 54. We're going to go ahead and do A. So if you remember and you look at your steps that you wrote down from the example, the first thing we're going to do is check and see, is this a linear relationship? Because I'm skip counting by 1s on the top. If I'm consistently skip counting by the same number on the bottom, I know it's linear. So if you go ahead and look here, you should be able to tell that we are adding 6.5. Every time that I am moving over down here. So that is my rate of change. So I'm going to go ahead and write out my equation here. So I'm going to say f of x, because I'm writing my function, is 6.5 times x. And then the last thing we need to do is find that b value. In this case, I can easily substitute and use one of the points here. But if you notice, because for 1 of whatever this is equals 6.5, that tells me that if I were to skip count backwards and find x of 0, I would also then have to subtract 6.5 and I would also get 0. So that means that this is a proportional relationship and that my slope-intercept is 0. So if we inspect that and check our answer, you would find that that function is correct. Go ahead and do problem B on your own and see if you can find the y value for problem B, and we'll check it in class. We have now moved on to page 55. We are now on example 3. So again, this example is not in your textbook, in your student companion, but you can take notes and then we'll do the practice problems after. Tamika records the outside temperature at 6 a.m. The temperature increases by 2 degrees Fahrenheit every 6 hours every hour for the next 6 hours. If the temperature continues to increase at the same rate, what will the temperature be at 2 p.m.? Our very first step is to write the function that models the situation. As you can see, our 2 is our slope, or our rate of change, because it is changing and increasing 2 degrees Fahrenheit every hour. -3 is our initial value, or our y-intercept, because at 6 a.m. that is the temperature it started at. My next step will be to sketch the graph. You don't have a graph paper in your student companion, but you can use one as separately if needed, or you can make a quick sketch of a graph so that you can do this. Notice that we're graphing the same way that we did in topic 2. We're using the y-intercept here as our first point, and then the slope of 2, rise over run, to plot any points that follow. You only need 2 points to make a line, so as long as you have 2 points, you should be able to draw that line. Also notice that because this is dealing with temperature, and because we are starting at -3 and increasing, my line does not continue in both directions. It's actually a ray that starts at -3 and then continues in one direction. This will change depending on the situation that you have. If you do not have a word problem, just assume that it's going in both directions. The last step we have, because down here it does ask us to find what is the temperature at 2 p.m. They're going to go ahead and replace x with 8 because the difference between 6 a.m. and 2 p.m. is 8 hours. When they do that and solve it, they find that y is 13, which means that if the temperature continues to increase at the same rate, which doesn't always happen with temperature, but if it does, then the temperature at 2 p.m. will be 13 degrees Fahrenheit. The graph y equals 2x minus 3 is a line. Therefore, now remember, highlighted words here, that means vocabulary. We need to write this down. That means that this function is a linear function, which is a function whose graph is a line. Continuing to analyze this linear function, we're going to go ahead and question if this linear function realistically represents the temperature of that word problem. If you think about it, because temperature is not usually a linear thing, we don't usually start at one temperature and continue to rise forever. This is not an accurate or realistic representation for temperature, because temperature usually kind of looks like a bell curve, right? We start cold and then we rise, then we kind of plateau a bit and then decrease. So for part of the day, this part that's circled, this graph will be accurate. It's realistic for a portion of the day. However, for the rest of the day, it's not going to continue to rise. That's unlikely, so it is not accurate. So when we talk about analyzing a linear function, we're really talking about just taking a look at like the word problem and seeing what matches, what makes sense. So in your book, we're now on page 55, and we're looking at the 2 examples of graphs. So again, you don't have graph paper, but if you can find some, or if you can sketch a quick graph, that would help you to figure this out. We're going to graph this the same way we would a slope-intercept form. We're going to go ahead and use the y-intercept positive of 1 to be one of our first points. And then we're going to use the slope of negative x, which is -1, to find my next point. So I'm going to start at my y-intercept, and I'm going to go down 1 over 1. So my line should, if I'm done it correctly, if my points are in the right spot, it should be a nice vertical line that looks like this. Check my answer, and you can see here are my points, my x and y intercepts. Go ahead and graph the next graph, and so we can check it in class. The last thing that we're going to do is go ahead and use these linear equations to solve problems. So our problem here is a chairlift starts at 0.5 miles above the base of a mountain and travels up the mountain at a constant speed. How far from the base of the mountain is the chairlift after 10 minutes? Okay. And here we're going to go ahead and write a linear function to represent the distance the chairlift travels from the base of the mountain. We're letting t equal the time in minutes. And we're going to calculate the speed. So because it tells us that the speed is in miles per hour, we have to convert it to miles per minute. So they go ahead and they take the 6 miles in 1 hour, and they times that by 1 hour, which is 60 minutes. So that tells me that our speed is actually 1/10 of a mile for every minute. They then write out this formula right here, which is our function. D of t, distance of time, is 1/10 times t plus the half of a mile that they started at. We are now going to compute this, and solve it for t, which we get 1.5.